so we started looking at optical isomerism last time. And basically, we just said it was a different form of stereoisomerism. So it occurs when compounds have no superimposable mirror images. I'm just going to try and get this to. So, so what I was saying was, so looking back over isomerism, like we were doing last time, just going to try and get this to a sensible size so I don't have to see myself. That'll be fine. That's better. So optical isomerism is what we were looking at last week. And basically, we said it was another type of stereoisomerism. And basically, what happens is when we have these non-superimposable mirror images. So basically, what we described that as is we basically said it was very similar to our left and right hands. They're the same. We have the same amount of fingers and thumbs on each, but actually, no matter how we rotate our hands, we can't get them to sit on top of one another and look identical. So for both our palms to be facing the same direction, if we put our hands together, our thumb will always be touching our small finger and our little finger always touching our thumb. We can't ever change that. So that's basically what optical isomerism is. So it gives you non-superimposable mirror images. And you basically get two forms of these optical isomers, and we call them enantiomers. And they occur when we have this chiral center. And if we'll recap a chiral center, but basically that chiral center was a carbon in the middle, and it has 4 different groups attached to that carbon. And it also has an asymmetric carbon atom. So when we have those 4 different groups, so basically if we had the same groups attached to it, we'd basically be able to rotate it in a way that then we would be able to get non-mirror images, and we'd be able to make just isomers of it and rotate it, make different ones. An asymmetric carbon has 4 different atoms, and it's often 4 different groups, often 4 different atoms, and they're arranged tetrahedrally around it. So this is an example of the chiral centers. So as we can see in the bottom left, there's 4 different colours arranged tetrahedrally about that carbon atom, and that's basically just happened to show that that's chiral centers. No matter then how we would rotate it, they couldn't be superimposable on each other. And then the same of the one on the right. So the one on the right, we've got 2-chlorobutane, and it exhibits optical isomerism, and that's because the second carbon atom has 4 different atom groups attached to it, and we've got them all identified here. We've got 4 different groups attached to each. So if we're going to spot a chiral center, you might get shown an image of it, and sometimes the images are really easy to spot a chiral center, or we might get something like this, which makes it a bit harder. We're going to have a talk about that now. So if we look at each carbon atom in this chain, and we're going to look at what it's attached to, so you could actually draw these out. That's what I'm going to attempt to do now. So draw, pen, here we go. So we've got 1-chlorobutane. So we've got CH3, CH2, CH2, another CH2, and then finally a Cl. So if we look here, we've got no groups here, if I highlight them, where it's 4 different ones. So if we look at this carbon, we've got 1 different group here, but then we've got a hydrogen, so it can't be that one. And then actually, if we look on either side of this, it's got identical groups on either side, so it can't be them. So the first carbon's got 3 hydrogens around it, so it can't be chiral. Second carbon's got 2 hydrogens around it, so it can't be chiral. Same for the third and same for the fourth. So that one can't be chiral. So if we look at the next example. Here we go. If we look at the first carbon, that one can't be chiral because it's got 3 hydrogens around it. If we look at the second carbon, again, it can't be chiral because it's got 2 hydrogens around it. Our third carbon, well, it's got a hydrogen, CH3 group, a chlorine, and a C2H5 group. So that is chiral. The fourth carbon isn't chiral, but it doesn't matter. We just need that one central chiral carbon involved. So yeah, so that one is chiral. If we then look at, oops, gone too far, but never mind, we'll look at both of them at the same time. These two, neither of them are chiral because again, if we're looking, we've got duplicates around them. So that's a good way for us to work it out. And again, you can always draw it out just to be doubly sure. So what do we actually mean by non-superimposable images? I've said the things that we can't stack on top of each other. So here we have an optical isomer. These are optical isomers. The non-superimposable mirror images. So let's have a look. What should happen? Okay, so some common objects that in a minute we're going to get a what's the word? A diagram that's going to show us how it works. Basically, some common objects that are non-superimposable mirror images. So something that's mirror image and superimposable are spoons, superimposable on top of each other, but they're not mirror images of each other are books. Non-superimposable mirror images are hands. Okay, so for optical isomerism in molecules, both conditions must apply. So they have to be mirror images and non-superimposable. So this is what we're going to see now. I don't know why it's doing this. Oops. Okay, so here we go. So this is our mirror image. And what's going to happen is it's going to move and it's going to rotate and it's going to show you how it's not superimposable. So if we rotate the molecules, so the red molecule is in the same place as the other red molecule, we're going to the same place, but it's not superimposable because the red goes with the yellow and the yellow would go with the red. So it's non-superimposable. We cannot stack one molecule on top of the other. So what are the differences in optical isomers? So isomers differ in their reaction to plane polarized light, which is what we spoke about before. And basically what we said is plane polarized light vibrates in one direction only. And optical isomers actually are able to rotate this light to the right or to the left, depending on the optical isomer. Rotation of light is then measured using a polarometer, and rotation is measured by observing the polarized light coming out towards the observer. So if the light appears to have turned to the right, that would be the D isomer, the dextro-rotary or positive isomer. Or if the light appears to have turned to the left, it's the latho-rotary or L or negative form of the isomer. And if you remember last time, we talked about race mates. So race mates is basically that we get quantities of these isomers occurring, and you might get equal quantities of them, you might get different quantities of them, but most of the time they actually occur in 50-50 mixtures, and it's very hard to make pure like pure solutions and pure I can't think of what word is that. Just to synthesize a pure isomer of just one type. So we often get a mixture. So that's a racemate. So a 50-50 mixture of the two enantiomers is a racemic mixture. The opposite optical effects of each isomer cancel each other out. So you don't have those optical effects. So then the plane polarized light will be going in that one direction only. It's not going to the left. It's not going to the right. It's going in that one direction only. So some examples of this is optical activity is really common in biochemistry, pharmaceuticals. So like we said before, lots of amino acids exhibit optical activity, and many drugs must be made of one optical isomer to be effective. So if we have both, it's not as effective in it, or it might not work at all. So we have to purify it. So either we have to purify it, so we make the racemic mixture and then get rid of the isomer we don't need, or we synthesize a pure substance. So basically, why we want these drugs to be only made of one optical isomer is we need smaller doses. It's safer and cost effective. If we have to give someone a huge dose to counteract the negative side effects. So when I was talking to you about morphine, one's addictive and not very doesn't give much pain relief. The other isomer gives good pain relief but is not addictive. And we'd have to give a huge amount to basically counteract one or the other effect. It's not safe to do that. It's also not cost effective. So we want to use the smallest amount of the drug possible. You're also going to get side effects of the negative isomer, or the isomer that we don't need. So for example, morphine, one's more addictive, you then get more addicted to it. And the pharmacological activity is just going to be improved. So optical isomerism, this is a polarimeter, which we talked about, which is how we measure that plane polarized light. So basically what's happening on this image is that we've got a light source, and basically this light source is producing light and it vibrates in all directions, okay? We're talking about plane polarized light here, so it's going to pass through B. So this light passes through B, and B is a polarizing filter. And what B does is it only allows through light vibrating in one direction. So from this image, it's up and down at 90 degrees. Then what happens is the plane polarized light passes through the sample, which is C. So this is our polarimeter part. Okay, so it passes through there, passes through our sample, passes through whatever we're wanting to measure. And D, if our substance is optically active, it will rotate the plane polarized light. So basically, B is just making it into a plane polarized light. C is what we're wanting to test to see if it's got any optical isomers in it. D is then our point where our light is going to rotate depending on if there's any optical isomers present or not. E, we're then using another filter. This is called an analyzing filter, and it's turned so that the light reaches a maximum. And then the direction of rotation is measured coming towards the observer. So basically at this point, if the light appears to have turned to the right, it's dextrorotary, or left labial rotary. So basically it tells us if there's an optical isomer in there, and then if it has turned left or right, which optical isomer it is. So it's actually quite nice and simple. We also spoke about how we can form them. So basically, it often happens with carbonyl compounds. I'm just going to move this so we can read this. And basically what happens is nucleophilic addition happens. And this is if there's two different groups attached to our carbon-oxygen double bond, the possibility of forming optical isomers arises. So we have the nucleophilic addition, in this example, of HCN to ethanol. So basically what's happening here is if the nucleophilic cyanide ion, which is up here in the, let's put my pointer on, up here in our blue and red, showing there, that's our cyanide ion, attacks from above, one optical isomer is formed. So that's one optical isomer. And basically the optical isomer is formed depending on which direction the ions attack from. And now my pointer is not letting me do anything else. However, if instead it attacked from the bottom, this gives a non-superimposable mirror image of the first. So then that's our two optical isomers that are formed. We've got two different mirror images, and they're non-superimposable. So it all depends on the direction of it being attacked from, depending on which isomer we get. So this reaction produces a mixture of two optical isomers because both modes of attack are possible, and one is neither favourable to the other. They're both exactly the same, and that would make our racemic mixture. So the nucleophilic addition of HCN to ethanol, here we go. The HCN, our cyanide ion, attacks from above. That bond breaks, and we get our first isomer, our first isomer being formed. Then what should happen in the animation, here we go, we've got the same ethanol being shown. Cyanide ion attacks on the bottom this time, and it produces the mirror image non-superimposable opposite isomer to the first one. So this reaction produces a mixture of the two optical isomers. This is lactic acid that we talked about last week. Lactic acid can be formed from ethanol in a two-stage process. So this actually links really well to respiration, actually, when we talked about respiration last week. So basically what happens is we've got ethanol to begin with, and nucleophilic addition of hydrogen cyanide to ethanol happens first. So that happens. And then we have hydrolysis of a nitrile group to get to the lactic acid. So during the first stage, a nucleophilic cyanide ion can attack from below or above the aldehyde. A mixture of the two enantiomers is then formed. Acid then hydrolysis of the mixture then provides a mixture of the two lactic acid forms. And that's just that hydrolysis which turns it to lactic acid, but we've already formed the two isomers by that point. This is, oh, what have I clicked on? Quick chat about thalidomide, which we talked about before. So it's basically, one obvious difference is how optical isomers respond to plain polarized light, but obviously they can actually affect biologically our bodies and show different chemical reactivity. So thalidomide, like we spoke about last week, is a chiral molecule, and it can exist as two enantiomers, so it's an optical isomer. 1960s, it was originally formed to treat anxiety, but was also used for morning sickness in pregnant women. However, this drug caused many children to be born with deformities and missing limbs. And it turned out that only one of the enantiomers, so the structure on the right, was effective and safe. Its optically active counterpart wasn't. And the major problem was that during manufacture, as we know, a mixture of the isomers were produced. So we get that racemic mixture. The one on the left wasn't effective, and it also wasn't safe. And that is what caused these deformities and missing limbs to occur in these babies. So this drug was banned worldwide, but actually it didn't get banned until tens of thousands of babies have been affected. It took a long time for them to realise why all of a sudden these babies are being born like that, and that link and that correlation had to be formed. A few other points about optical isomerism before we go on to a few uses of it as well. The formation of a racemic mixture is actually more likely in a lab than in a chemical process occurring naturally in the body. If a compound can exist in more than one form, only one of the optical isomers is usually effective, and the separation of isomers will make manufacturing more expensive. So a drug made up of both isomers will require a larger dose and may cause problems if the other isomer is poisonous, like thalidomide. So that's a really good, interesting point. Right, I just need to change what I'm sharing with you. Let's go here. So let's just move a second. We've done that. Okay, so optically active compounds. We've done quite a lot of these optically active compounds. Actually, we did all of them, I think. Stop looking at that. Next. Trial catalysts. Yeah, no, we did all these. I think this is where we've got to now. Just waiting for it to load. Okay, so practical techniques. So basically what we're going to look at is how we basically get these optical isomers on their own. So, or how we make these optical isomers. So we're looking at organic synthesis now. So organic synthesis is when we're going to make an organic, so a carbon containing compound. So if we're hearing the terms organic chemistry, we're thinking, oh, hang on, what does organic chemistry mean now? It's a compound that contains carbon. So organic synthesis is that process of making organic compounds via organic reactions. So the synthesis of a single organic compound can involve multiple steps, with each step being a different reaction. So in the lab, if we carry out organic synthesis, it involves lots of different equipment and techniques. And actually, we're going to just basically go through lots of these different techniques that you might come across. Most of them will be quite familiar. Lots of them won't be very different or new. So we'll probably go through these at a swiftish pace. It's nothing really too in-depth. It's just sort of a bit of a recap. And you can always spend a bit of time later just having a bit of a look back through them. But it's nothing really too complicated. But this is a bit that I'm going to go through. The glassware that we often use, or professional scientists often use in labs for organic synthesis in small scale labs, is often known as quick fit. And that's because the joints of each piece of equipment are a standard size. Different pieces of equipment can be fitted together really easily. And that's really important because, as we said, each step can involve us needing to do a different type of reaction and a different, method for each different step. So we actually need all the different components and equipment to be able to be interlinked to each other and change very, very easily. So few key techniques that are used to make organic solids includes heating a reaction under reflux, and that's to prevent volatile chemicals from escaping. Distillation, so that heating of a liquid to separate mixtures of liquids at different boiling points. So that's prep of an organic solid. So we've got an organic solid, we need to do something with it. So we're either going to get rid of it, prevent volatile chemicals escaping, or distill them to get different, separate them out. Purification, we could use filtration of a solid product from its liquid reaction mixture under reduced pressure. We might use recrystallization of the solid to remove impurities. And we might use determining the melting point of the pure solid to use that to then purify it. So heating under reflux. Lots of organic reactions are really slow. And if we left them to happen on their own in a lab, it would be really useless, pointless, and cost us a lot. So we need to heat them to speed up reaction. However, the side effect or a negative to this is actually lots of organic compounds are very volatile and they evaporate really, really easily when they're heated. So what we do is we do speed up reactions using heat, but we heat them under reflux. So when we heat something under reflux, basically when we have a condenser attached to it. So a condenser has that cold water flowing through it. As you can see here, we've got a flask. We're going to apply heat to it with the liquid inside it. And then we have that condenser, water in and water out. And it has cold water flowing through it constantly. So what happens is, as the reaction in that flask at the bottom is heated, so as that reaction mixture is heated, any vapors that have evaporated hit the cold condensing walls, they form back into the liquid and fall back into the reaction mixture to continue reacting. So here we're not separating anything, we're wanting a reaction to happen. We don't want to lose any of that mixture that we're causing the reaction to happen. And basically what happens if we heat it, it becomes a gas, it evaporates quickly. We don't want to lose any of that mixture. So if we put a condenser there, it means that the evaporation, the gases will hit the side, it will condense and then go back into the mixture. And actually it will mean it will keep reacting as well, because sometimes what can happen, it'd be one of two. It can be our products that do that, or it can be our reactants that do that. So either if we didn't do that, we would lose product, or we would lose reactants, or we could lose both. So that's one thing, heating under reflux. Another thing we could do is distillation. This is going to be like a really quick recap of distillation. I know you've done distillation lots, but distillation is where we've got a mixture and we're going to separate a pure liquid from a mixture of liquids, or multiple pure liquids really. So let's have a quick look. So basically distillation, I mean, you can do lots of different types of distillation. You'll have heard of fractional distillation, where you can get different liquids out at different points of heat in a big fractional distillation tank, but this is your basic lab distillation we're talking about here. So, got our distillation apparatus set up. And basically we've got our flask with our ethanol water mixture in it. We've got a thermometer at the top. Now that thermometer is really important because we're wanting to heat until a specific temperature, okay? And it's going to be until that temperature of whatever we're wanting to remove or separate is its boiling point. We've obviously got the condenser, because if we didn't have a condenser, we would cause the liquid to evaporate, that mixture to evaporate, and then it would sort of have nowhere to go. So, or it would come out the tube and then it would just go into the air. So we have the condenser to do exactly the same as heating under reflux, but this time we've added a separation technique into it. So it's basically like heating under reflux with separation. So condensing tube has water in, water out, and then obviously we've got a collection beaker at the end. So ethanol, as we know, has a lower boiling point than water, so it evaporates first. So we heat it, and when ethanol's boiling point, 78 degrees, is reached, the gaseous ethanol rises from the flask, as you can see. So we've got that gaseous ethanol rising into flask temperature. Thermometer is always good to make sure that we're not heating it too high, otherwise we can miss that point, heat it above and go to the boiling point of water, and then we just end up at the end with a beaker of a mixture of ethanol and water again, and that would have meant our whole process was pointless. So heat it until 78 degrees, and our gaseous ethanol rises from the flask. As that happens and it goes down the pipe, the gaseous ethanol hits the cold inner surface of the condenser. It condenses back into liquid ethanol and drops into the collection flask at the end. So, stage 4, once all our ethanol has evaporated, only water is left. So what we do then is we turn the heat off and the apparatus returns to room temperature, and our ethanol and water solution has now been separated. We can actually do filtration. Filtration, we often think of a filter funnel and a solid and a filter paper, which is fine, but we can also filter under reduced pressure. And this is where we use a special type of funnel called a Buchner funnel. And this can be used to filter a solid product from a liquid reaction mixture. So that's basically where a solid has formed from when we've reacted two liquids, but we've got some excess of liquid reaction mixture left. So what happens is a piece of rubber tubing connects the Buchner flask to a vacuum pump. The vacuum is switched on. So basically we've done the filtering and we've got that at the bottom, okay? And so the vacuum is switched on and a piece of filter paper is placed inside the Buchner funnel. The reaction mixture is slowly poured into the Buchner funnel. The vacuum sucks the liquid through the funnel and into the Buchner flask. The beaker is rinsed out with solvent to make sure all the solid is transferred to the funnel, and the solid is left to dry under vacuum for a few minutes. So it's very similar, but we've just added that extra part of the Buchner funnel to it. So then we can have recrystallization, and this will be a very familiar technique. So impurities in a solid product can be removed by recrystallization. So this technique relies on pure product and the impurities having different solubilities in a given solvent. If they don't, it doesn't work. So what we do, like any recrystallization method, we heat our solvent, and our solid is dissolved in the minimum amount of hot solvent. If we start having excess, it makes it really complicated. So we dissolve our solid in the minimum amount of hot solvent. It needs to be a hot solvent as well. The solution is then allowed to cool, and crystals of the pure product will start to form while the impurities remain in solution. Then we can filter the mixture under reduced pressure to obtain the dry pure solids. Basically, this technique we just talked about before, we then go through that. So that's a really good one as well, to get a pure solid from an impure solid. Melting point ranges, so this would link very similarly to, it's very similar in a way to, what's the word I'm looking for, distillation, but we're looking at melting points, so we're looking at solids this time. So after a solid product has been purified, its melting point can be measured to determine its purity. So we'll have set boiling points, melting points for solids. The purer the solid product is, the closer it is to this set key melting point. Further away it is, either above or below, means that it's less pure. It's still got some of the other compounds with it. So a pure product has a sharp melting point. It has a small melting range of 1 or 2 degrees. The melting range is a difference between the temperature at which the solid starts melting and the temperature at which the solid has fully melted. An impure product melts over a wide range of temperatures. So actually it's probably showing us that we've got something that maybe melts a bit sooner or a bit later, depending on, I say sooner or later because of how long it would take to heat something up, but something that melts to lower or higher temperature. An impure product also has a lower melting point than a pure product. So that's always really important to remember. The melting point determination. So to prepare a melting point sample, so this is something that's that given sample I was just saying. So I was like, oh yes, we're going to compare it to this. What we do is the open end of the melting point tube is dabbed in our solid sample, and it forces some of the solid into the tube. The tube is then placed on top of the melting point apparatus, and this apparatus is set up so that it starts rapidly heating up. The sample is observed through the window. The temperature at which the solid melts is noted. And this whole process is repeated with a fresh sample, but this time the heating is slowed down as the melting point is approached to obtain a more accurate value for the melting point. And that is those techniques. Let me go back to that, make that smaller. And one more little bit about isomerism. So that links to the isomerism. So the point of that was basically different ways that we can get those racemic mixtures on their own. And what we're going to have a quick look now is organic synthesis again, synthetic routes, how we might devise synthetic routes, how to make an organic compound. Okay. I'm not going to go through all the different functional groups at the minute. I will actually, just as a quick reminder, these are all our different functional groups. So we have alkenes, which remember is a carbon-carbon double bond, have carbon-carbon double bonds. Alcohols, which have our OH group. Aldehydes, which have our COH. Ketones, C double bond O. Carboxylic acids, COOH. Acid chlorides, COCl. Acid anhydrides, nitrile groups, esters, nitros, amines, phenols, amides, and azos. These are things that you'll get asked a lot all the time, so it's always good just taking your time to learn the different functional groups and looking at what synthetic routes can help us with this. So I'm actually going to pause there for a minute. I know that makes no sense because it's like, oh yeah, we'll do this. I actually want to look at alkanes really quickly. I knew there was some logic behind this. So stop share a second because I don't know what I'm sharing anymore. Chemistry of alkanes. Here we go. So I just want to spend some time going back over alkanes because I know I've just basically gone on about isomerism and the uses of optical isomers and then ways that we can maybe split them. And before going on to synthetic routes, I actually think we'll spend some time actually looking back over some of those organic compounds, some of those basic organic compounds. So I want to look at alkanes to start off with. So we're going to look at a quick recap of what alkanes look like, the physical and chemical properties, how we break covalent bonds, chlorination, and then cracking. So alkanes, basically, they're a member of a homologous series, and they have a general formula, which is CnH2n plus 2. And that's for non-cyclic alkanes. And they are saturated hydrocarbons. So that basically means all of our carbon-carbon bonding is single bonds, and they're spaced tetrahedrally about our carbon atoms. There's no carbon-carbon double bonding involved. There is isomerism involved in alkanes when we've got more than 4 carbons present. So here we go. We've got an example of a structural isomer here. This is with C4H10. If it is as an unbranched chain, it would form butane. But once we get more than four carbons or more, we can start having branched chains being added. This means that then obviously we've got lots of potentials of different isomers being formed. So then, for example, butane, if we then have C4H10 with 1 branched chain, we can actually then have 2-methyl propane. As we've just said, structural isomers, they have the same molecular formula, but they have a different structural formula. They possess different physical properties, such as boiling point, melting point, and density. So that's really important to remember. Structural isomers have different physical properties. So, hybridization of orbitals. We're just going to skip this because we don't really need that right now. Basically, actually, I'll keep this up for a second. It's basically talking about why alkanes make a tetrahedral shape. So we always go, oh yeah, alkanes are arranged tetrahedrally, or why? Okay, so let's look at carbon. So we did this ages and ages ago. So the electronic configuration of a carbon atom. So if we think back, electronic configuration, so we're looking at our electrons and what orbitals they sit in. So the electronic configuration of carbon atom is 1s2, which we've got here, 2s2, and then 2p2. Okay, so if you provide a little bit of energy, what we can do is we can promote and lift one of those s electrons, those 2s electrons, into a p orbital. And our electronic configuration would now become 1s2, 2s1, and 2p3. This is actually favorable because of the arrangement of electrons. 4 unpaired with less repulsion is more stable than 2 paired. So why is this important? So the 4 orbitals, an s and 3 p's, combine or hybridize, and they give 4 new orbitals. And basically what happens, why this is really good, is basically all our orbitals become equal and they're equivalent to each other. So because 1s and 3p orbitals are used, it's called sp3 hybridization. So this is what occurs. So we go from 2s2 to 2p2 to this, and we get 2s1 and a 2p3. So we get 4 orbitals now instead of 3, and it becomes this 4 sp3 orbitals, and they are equivalent, so they all look identically the same. So this is the tetrahedral shape and why I was going on about that. So in alkanes, that 4 sp3 orbitals of carbon, what they basically do is they repel each other equally. If we'd got that full s orbital, it wouldn't cause the same equal repulsion. But because we've got these 4 sp3 orbitals of carbon, they repel each other equally into this tetrahedral shape. And it has an arrangement with bond angles of 109.5 degrees. So each sp3 orbital in carbon overlaps with the 1s orbital of a hydrogen atom to form a CH bond. So this is what's happening there. That's that overlapping. It's basically the grey circles with the orange shape. So alkanes, what are their physical properties? As you add more carbons, the boiling point increases. Makes sense. More atoms, means we've got a bigger induced dipole-dipole interaction, greater intermolecular force, takes more energy to separate the molecules. We need more energy required to break those molecules, therefore they've got a higher boiling point. So that's why it increases. So as you can see here, CH4's got a boiling point of minus 161, but C4H10 only got a boiling point of minus 0.5. So the difference gets less. The mass increases by smaller percentages. Also, chains. So straight chain molecules have greater interaction than branched. So basically what's happening there is there's more, what is the word I'm looking for? Shielding going on. So there's the boiling point is higher. The more branching you've got, there's less shielding, there's less of those intermolecular forces acting on it. So it means less energy is required to break those bonds. The branches are the first things that will get broken off. And then you've got a smaller unbranched chain, which then requires the bonding. So C5H12, if you have it as a long unbranched straight chain, has a higher boiling point than the most branched chain of it you could get. So physical properties. So we've talked about the boiling point, the melting point. Again, this increases in molecular mass, but it's not, the trend isn't as regular as the boiling point. Solubility. Alkanes are a non-polar substance and so are immiscible with water, and they are soluble in most organic solvents. Oh. So chemical properties. Alkanes are fairly unreactive. They're quite strong. They're almost nonpolar and they involve single covalent bonds. They don't really have any site source that encourage substances to attack them, which makes them, again, highly unreactive. We can use alkanes for combustion. So alkanes are really good as fuels, especially those lower members of the series, and they react with oxygen and create an exothermic reaction. So we can have complete or incomplete combustion, which we've talked about before. And the greater number of carbon atoms, the more energy which produce, but the more carbon atoms, the more oxygen we need for complete combustion. Therefore, if there's not enough oxygen available, you're more likely for incomplete combustion to occur. So that's quite important to remember. This is quite a good tip. If you're balancing an equation involving complete combustion, remember, every carbon in the original hydrocarbon gives one carbon dioxide, and every two hydrogen atoms gives a water molecule. So if you put all your numbers into your equation, you count up your oxygens and hydrogens on the right-hand side of the equation, then you'll balance the oxygen molecules on the left-hand side. Pollution and alkanes. Basically, combustion. Alkanes are good for combustion. However, combustion gives rise to a lot of pollutants. Example, things like power stations, they give off sulfur dioxide. These are emissions that can produce acid rain. Internal combustion engines give off things like carbon monoxide, nitrous oxide, and unburnt hydrocarbons. So these are all really actually harmful to people and harmful to the environment. So what we need to then do is, if we're going through these combustion processes, we need to remove those harmful pollutants. So sulfur dioxide, we can remove that by reacting the effluent gases with a suitable compound, so something like calcium oxide. Or if we're trying to remove carbon monoxide and nitrous oxide, we pass these exhaust gases, because these are what are found in cars, through a catalytic converter. So years ago, cars didn't used to have these, and the pollutants coming out of cars would be far worse. And if you go to places like London, they have like pollution zones, and certain cars can't go into those areas. I think you used to have to pay extra to be able to drive certain cars and vehicles that didn't have catalytic converters in those areas. Now I'm not even sure if you're allowed to drive them. So basically, what a catalytic converter does is it converts carbon monoxide to carbon dioxide, nitrous oxide to nitrogen. And then any unburnt hydrocarbons that are hanging about are converted to carbon dioxide and water. So these catalysts are made up of finely divided rare metals, okay? And leaded petrol must not pass through the catalyst, as the lead deposits on the catalyst surface and poisons it and blocks the sites for reactions to take place. So that's why all our petrol that we get at petrol stations is unleaded petrol, because otherwise leaded petrol will break our catalytic converters, and then all these harmful emissions won't be converted to better emissions. And I know we always go, oh, carbon dioxide, too much carbon dioxide in the atmosphere is bad. It is bad. However, it is a lot better than carbon monoxide. It's still really bad for the environment, but it's a lot better than carbon monoxide. So covalent bonds, how do we break them? There's 3 ways we can break them. The shared electron pair and unsymmetrical covalent bond, we can either go with unequal splitting. Unequal splitting basically means that one of the atoms gets all the electrons, the other doesn't get any. So in this situation, we're going to produce ions, and this is heterolysis or heterolytic fission. Or we can have equal splitting, and this is where we produce radicals, sometimes known as free radicals, and that's homolysis or homolytic fission. Okay, so if several bonds are present, we always are going to be breaking that weakest bond first. So whenever we're looking at something that we're breaking down, the weakest bond that is present is always broken first. Energy that breaks bonds comes from lots of different places, heat and light, for example. And in a reaction between methane and chlorine, we could use either. However, in the lab, a source of UV light is favoured. So free radicals, what are they? Basically, they're a reactive species of atoms which possess an unpaired electron. And their reactivity is due to them wanting to pair up the single electron. And we form these, like we just said, by homolytic fission of covalent bonds. So the covalent bond has been split unequally. We formed, no, we haven't split it unequally, we split it equally. So both of them have become radicals. And these are formed during reaction between chlorine and methane. They also form during thermal cracking. And they're involved in reactions that take place in the ozone layer. So here's an example of chlorination of methane. So reaction of chlorine and methane together needs to be under UV light or sunlight. Heat is also an alternative energy source. So what can happen? Depending on what's going on, we can form chloromethane, dichloromethane, trichloromethane, tetrachloromethane. Basically, free radicals are really, really reactive, and they're trying to pair their electron with a sufficient chlorine. Every hydrogen will eventually be replaced. So mechanisms, when we talk about the word mechanism, it's what we think is going on, and the reaction tells you exactly what's happening. So chlorination of methane, so when chlorine and methane react, proceeds via free radical substitution. And what this means is the methane is attacked by free radicals, and this results in hydrogen atoms being substituted. And basically what happens is in the chlorine, and the chlorine is broken down and it's split. Split forms free radicals by homolytic fission, and results in hydrogen atoms being substituted by chlorine atoms. Okay. And this process is a chain reaction. And in the propagation step, one radical is produced for each one used. So here we go. So initiation. So we've got Cl2, and we've got this homolytic fission occurring, okay? So Cl2 gets broken down into 2 chlorine free radicals. So during initiation, the weakest bond is broken because it requires the least energy, okay? There are 3 possible bonds in a mixture of alkanes and chlorine. So we could have carbon with a hydrogen, 2 carbons, or 2 chlorines, okay? The chlorine-chlorine bond is the weakest, so that is the one that is broken. It's only got bond enthalpy of 242 kilojoules per mole, so it's the weakest, requires less energy to separate, so that's why that happens. So then propagation, that's our next stage. So free radicals, as we said, are really reactive. So what happens is we've got a chlorine free radical, and it reacts with CH4 because they want to pair up and share their electron, the single electron. They don't want to be on their own. So if you do this by abstracting a hydrogen atom from methane, so basically what happens is they join with a methane, they get a hydrogen atom, and then what forms is a methyl radical is formed. Methyl radical, as we can probably guess, is also very reactive and attacks a chlorine molecule. And a chlorine radical is produced and the whole process can basically start over again. So it's cyclical. So we've got a chlorine radical, joins with methane, we make a methyl radical. Methyl radical reacts with chlorine, that makes chlorine radical, and it just goes again and again. So radicals are used and then they are regenerated constantly. So that is how this works, this chlorination. Termination, it does eventually end. This is when the radicals are removed. So removing the reactive free radicals brings an end to the reaction. This isn't very likely at the start of reaction because of their low concentration, but as the reaction goes on, there'll be more and more radicals present, which means they're more likely to meet up. So what can happen in termination is it could be the chlorine and the chlorine free radical to join, form Cl2. We could have a chlorine free radical and the methyl free radical joining, or we could have the two methyl free radicals joining together. So basically, they're not very reactive. Alkanes need something reactive to persuade them to react. Free radicals need to be formed by homolytic fission of covalent bonds. So that's that equal splitting of those covalent bonds. And this is done by shining UV light on the mixture, but we could use heat. Chlorine radicals are produced because the chlorine-chlorine bond is the weakest, and you only need one chlorine radical to start things off. With excess chlorine being present, you get further substitution and a mixture of chlorinated products. So initiation, our radicals are created. In propagation, radicals are used and then regenerated. And then finally, in termination, our radicals are removed. So here we go again. If excess chlorine is present, what can actually happen is further substitution can take place, and this shows the propagation steps for that formation, so it can keep going and keep going. Basically, then we can start forming dichloromethane, trichloromethane, tetrachloromethane. And because of these many possible reactions, we will basically make a mixture of products from this. It's not going to be a pure substance. So individual haloalkanes can then be separated by fractional distillation. Cracking. So cracking involves the breaking of carbon-carbon bonds in alkanes, and it converts heavy fractions into higher value products. So we need a thermal catalytic, and it proceeds via free radical mechanism and proceeds via carbocation. So thermal, if we're going through thermal cracking, we want high pressure, high temperature. Our free radical is our mechanism. We're going to use homolytic fission, that equal splitting of those electrons when we break that carbon-carbon bond. Produces mostly alkenes. So for example, ethene for making polymers and ethanol. Also produces hydrogen, which can be used in the Haber process and in margarine. Bonds can be broken anywhere in the molecule by carbon-carbon bond fission or carbon-hydrogen bond fission. If we use catalytic cracking, we don't need very high pressure, but we do need high temperature. We use a zeolite catalyst. Our carbocation is our mechanism. We use heterolytic fission, so that's obviously going to make that unequal split. So we're going to produce branched and cyclical alkanes, aromatic hydrocarbons, and we're going to use this for motor fuel. So zeolites are crystalline aluminosilicates, and they're a clay-like substance. So we will leave that there. Let me stop recording.